Okay, welcome back friends. Welcome to another lecture on quantum field theory and quantum entanglement. Last time we were looking at the Dirac equation, the Dirac Hamiltonian, and then we moved to define meaning the wave functions, the static wave functions, and we also did the inner products and the outer products, which are essentially the orthonormal conditions, and these are the matrix equations. So the outer products are essentially the completeness relations. And along the way I started mentioning using the Noether's theorem for symmetries and conserved quantities essentially on the Dirac-Lagrangian. Then we looked at a couple of translations, essentially one is the space-time translations which conserves the energy momentum tensor, and then there is the Lorentz transformations which conserves the boost and which is also conserve the space part of the energy momentum tensor, and also it gives you the internal angular momentum of the Dirac equation. Before going further, let us look at a couple of more transitions before going to today's lectures essentially. The one is the one on vector symmetry. Okay, let us imagine the vector current of Dirac spinors. Okay, the vector spinors, we have seen it in the bilinear covariants. We have seen this vector current to be J mu vector psi bar gamma mu psi, and we showed that it transforms as a vector under Lorentz transformations. Now this is important to us as we will transformations. Now this kind of currents are important to us when we start looking at interactions for the Dirac equation essentially, or for Dirac particles. Okay, now this current, as we can see essentially, which is we can it is this current is very interesting and it has some properties essentially. Okay, and this property is essentially conservation of electric charge and electric current and everything. This property conserves electric charge. Okay, it conserves electric charge and currents. So this vector current is exactly very similar to the Klein-Gordon current which we wrote down, or the for the Klein-Gordon current, I think it will be something like phi star del mu phi minus so on. So this is very similar to that, but with the Dirac particles, instead of a del you have a gamma mu essentially. Now in the Klein-Gordon case, we know that it conserves electric charge because it is related to the charge of the particles. Here too it also is related to the charge of the particles, and this can be seen. The important point is conservation. How do you know that it gets conserved? So if you take the derivative of this, let's go to del mu psi gamma mu psi plus psi bar gamma mu del mu psi. Now this is just integration by parts the product rule of the differentiation, and now this is, if you use the equations of motion, this gives me I m psi bar psi minus I m psi bar psi, which is equivalent to 0. So it shows you this vector current is conserved. This vector current is always conserved because it is a difference of the mass terms essentially, and with the same mass and everything. Now the conserved quantity this symmetry from this current, I will talk about symmetry in a minute, is q is equal to integral d cube of x psi bar gamma 0 psi, which is nothing but integral d cube of x psi diagonal psi. This is nothing but the conserved charge. So this is the conserved charge. The space part is the conserved current essentially. Gamma I part is the conserved charge. Now this can be related to a symmetry, which we will see when we are doing interactions essentially. This can be related to the symmetry of internal symmetry. Symmetries of the Dirac particles, like one of the simplest example is psi bar going into e power I alpha times q times psi of x. Okay. So the wave function or the Dirac particle, you have an arbitrary parameter. So this is an arbitrary parameter alpha, and q is some integer. So let's take it to be an integer. It could be 1 for electrons and 2 by 3 for something, or some bunch of particles essentially. If the psi of prime transforms as e power alpha of q times q, an arbitrary phase transformation, then this is a transformation. It's an internal symmetry because you are not changing external, like you are not doing any Lorentz transformations, or you are not doing any space-time translations. Okay, this is an arbitrary internal phase transition of the wave function essentially, internal, and the Lagrangian is invariant. You can check that the Lagrangian is under this thing. So this conserves the electric charge. This symmetry transformation sometimes called gauge symmetry transformations or global gauge symmetry transformations. So these are called global gauge symmetry transformations. Conserve the vector current. So the current conserved is essentially the same, but similarly like in, okay. So what current is conserved under this symmetry transformations, you can ask that this conserved quantity is nothing but your vector current, which corresponds to your uh, electric charge and electric current and these parameters. Exactly. Okay. So this is different. This kind of vector current is different compared to, say, for example, this kind of vector current is different compared to space-time currents. And this is an internal current essentially. This is an internal current. This is an internal probability current, or it's more currently it's electric charge current essentially. You can do the same thing with axial symmetry. And axial currents. So instead of putting e power psi going into e power alpha, we put just an arbitrary parameter q. You can also put in gamma 5 on the top times psi. Okay, gamma 5 on the top. Okay, so this would mean, and so psi bar transforms as psi bar goes to minus alpha phi gamma phi. Okay, now this psi bar goes as e power alpha phi gamma phi. Now this will be conserved only when gamma phi dagger, which is minus gamma phi. So, this will be just phi only when m is equal to mu c. Okay. Now, this can be seen clearly when you express psi in terms of psi plus psi minus or else the chiral states essentially. So, psi plus is equal to u plus u minus or psi is equal to psi plus psi minus. When you do that, so there are two symmetries, one corresponding to the left moving particles and the one corresponding to the right moving particles. They are conserved under the Lorentz symmetry. They are conserved under the axial symmetry or the chiral symmetry. This is also called the chiral symmetry. Now, this is okay. Now, you can define this thing J mu, in this case axial, A is equal to psi bar gamma mu gamma phi psi. This we already know, this is the bilinear axial vector current essentially. Okay. Now, how do you know? Now you can apply the derivative of this current, that gives me psi bar gamma mu gamma phi psi plus psi bar gamma mu gamma phi del mu psi. Now, this is equivalent to, now you see this now you can use the relations and the equations of motion, and this will give me 2 I m psi bar gamma phi psi. So, this is the axial vector axial current essentially, this is the pseudoscalar current essentially. Now, the derivative vanishes only when m is equal to 0. When m is equal to 0, the derivative vanishes, and that is how you can conserve the axial vector current essentially. Otherwise, the axial vector current is not okay. So, these things are important essentially. At some point, this in quantum field theory, the axial vector currents play an important role in quantum field theory. Especially if you are considering higher order corrections, and so when corrections are considered. So, what did we learn today? Actually, so what we learned was that there are these symmetries which are essentially the global gauge symmetries e power I alpha q, which lead to conserved quantities. If it is simple thing, it leads you to vector current, and the vector current is independent whether the mass is 0 or not 0. Okay, independent of that, vector current is always 0. And what we will see, one of the first interactions we will see with Dirac particles will be this type, essentially this kind of vector like currents essentially, which will be conserved. So, the examples I gave are the electric charge and electric current and everything. So, now I described this global gauge, but you can also make it much more concrete. You can also say that that this gauge transformation works at every space time point. In such a case, alpha will become not an arbitrary parameter, but as a function of x. Okay. In that case, it is called a local gauge transformation. In that case, interactions will appear automatically. You introduce interactions by symmetry transformation properties essentially. We will see that when we come to interactions, before that we had to do quantization essentially. Okay. So the second class we have seen is axial symmetry and axial currents, also called chiral symmetry. Okay, because in this case the generator of the chiral transformations is gamma phi. So you put in gamma phi e power I alpha gamma phi, and then you see that in the limit, the massless limit, this axial vector current is conserved. Now notice that in this limit actually the Dirac spinor is independently written in terms of two components, essentially two Weil spinors, or if you want to call it the chiral spinors, or two component spinors. So independently you will have in fact two chiral transformations, one for the left handed and one for the right handed. Okay, good. And finally, as a parting shot, we mentioned that these axial vector currents play an important role in quantum field theory, especially when higher order corrections are considered. Okay, good. So let's stop here, and we will move slowly towards the interaction part. But before that, we had to do the quantization of the Dirac equation essentially. Okay. So Dirac fields. Okay. Now the Dirac equation has exactly the same problems, like it's a okay, as the Dirac wave functions have the same problems as say Klein-Gordon, in such that in the okay, as in the such that in the relativistic field theory, in relativistic quantum mechanics, there are multi-particle solutions. So you cannot get rid of negative energy solutions. Solutions, etc., etc., and there are then you have all these problems. So you had to do a quantization of the Dirac field. So if you just neglect, say, so I neglect the negative energy solutions, I'll do scattering theory with this, you'll end up with the same problems as in like Klein paradox and so on. So as we have seen in examples like the Klein paradox and Zetter-Bitter-Gang, and all these problems will always there. So there is no other option, but we have to quantize the Dirac field essentially. Now we would like to quantize the Dirac field exactly in the same way like we have quantized the Klein-Gordon field. Now the question is can we quantize the Dirac field exactly in the same way as we quantize the Klein-Gordon field? Okay. Quantize the Klein-Gordon field. Now, okay. Now the Klein-Gordon field, how did we quantize it? We wrote it in, especially we wrote it in terms of modes, then imposed harmonic oscillation condition, meaning this momentum modes, and then we imposed the harmonic oscillation quantization conditions, and then this has been replicated in terms of this commutation relations on the field and the conjugate field, essentially the conjugate moment of field essentially, and then these commutation relations, you using this, we check that we can build the entire the states, essentially multi-particle states of the field. That is how we quantized it. Now we will assume that we will do exactly the same way. Let us assume so, and the only complication here is these are spin half particles. Okay, let us assume that it can be done so. That it can be done for Dirac particles also. Remembering the complication, keeping in mind, okay, we have to keep in mind these are spin half particles. Now spin half particles are fermions, which we know, but will it lead to some complications when quantization? Because yes, it does actually, as we will see. Okay, it does, because these are fermions. Fermions always obey Fermi-Dirac statistics. So you are bound to expect some complications, because if you are building a multi-particle state, so if you are building, you remember that in for the scalar field we build an n particle state by just by applying a dagger, a dagger, a dagger, a dagger on 0 on the vacuum. Can we do the same thing here? Because then you have putting several bosons, meaning several scalar fields in one scalar particles in one state essentially, but in a fermionic field you cannot the fermions cannot occupy, okay, they cannot occupy a single state essentially. Fermions cannot occupy a single state, so multi-particle states will be a complicated issue. So how to proceed is the question essentially. Let us just proceed like we are dealing with a bosonic field or the scalar field essentially. Let us assume, but keep this in mind that these are particles essentially, these are fermionic particles. Okay, so the Dirac Lagrangian L Dirac okay. Now let us do a momentum, the conjugate momentum, because this is what we need. Psi dot, so this is I psi bar gamma 0 is called psi dagger. Now psi dagger, no time derivative, it does not have a time derivative of psi. Okay, so but that is because it is a first order equation in time essentially, because the Dirac equation. So we immediately promote this thing into what we want as the equal time commutation relations. Which we have done for the scalar field essentially. Let us exploit meaning impose these equal times commutation relations for quantization conditions. So this you have psi alpha of x, okay, alpha is the component of the spinor, and then psi beta of y, commutator is called 0, and the main important thing is psi alpha of x psi dagger beta of y, this should be equivalent to delta alpha beta delta cube x minus y. No, this is the imposition, this is the main thing, right, essentially. So we want to put a commutation relation between them. And similarly you also have psi al bar alpha of x psi beta of y is equal to 0. Okay. Now here I am imposing commutation relations using commutation relations. So okay, since I am using commutation relations, okay, and because it's a Fourier theory, we can write plane wave solutions, expand in terms of plane wave modes. Essentially, this each we expanding the fields operators. So remember that we are using exactly the same thing what we did for the Klein Gordon field operators in terms of plane wave modes and with coefficients which are essentially the spinors, and then there is the operator alpha, okay, corresponding to the harmonic oscillator with the spin is equal to 1 to 2 d cube of p cube AP. This is required for the Lorentz conservation essentially. So this is BP S, these are the operators U of S of P e power IPX plus C bar P of S V of S P e power minus I P dot x. So what we did, we expanded in terms of this spinors, negative energies, positive energy, spinors with plane wave parts, and B and P are the two operators, ladder operators, okay, creation annihilation operator, whereas this is a creation operator, the dagger, and this is an annihilating operator. So on vacuum, psi of x annihilates particle and creates an antiparticle essentially. That is a basic expansion we have done, okay, and each comes with its spinor wave function, okay. This is the expansion in modes we have done, and this B and P are, we need two sets of creation annihilation operators. So we chosen them as two of them, essentially B and P, B and C, okay, because the Dirac field has 4 degrees of freedom. So for each 2 degrees of freedom, you need two sets of creation and annihilation operators, and one is essentially the spinor contains the spin operator, and the creation and annihilation from the momentum state is created by this. We need two of them, so BS and B and C ladder operators take care of the 2 degrees which are for the positive frequency and the negative frequency. So, now you can think of the same thing with the psi dagger of x. So, this is for spin 1 to 2, spin states 1 and 2, this is essentially plus half and minus half to EP. So, let me just move it a little bit down, yeah, to P. Now, you have dagger US P e power minus P dot x, okay, plus Cp of S Vs P dagger e power plus P of x essentially. So, now you notice that B dagger is the creation operator associated with the particle with a spinor U of S, plane wave factor e power minus Px, and C dagger in the top equation essentially gives you an creates an antiparticle essentially. Okay. Okay, now so we have expressed it everything in terms of the creation and annihilation operators. Now what we will say is that these set of equations mean that BP, the relations BP are B dagger S Q. So B operator with P momenta and S R spin, and B operator dagger with spin S and Q momenta is equivalent to 2 pi cube delta RS delta 3 P minus Q. So that means you have satisfying A dagger like relations for this set of operators essentially commutation. But the fun part comes when you consider the C also, okay, the second part. Turns out if these equations have to be consistent, if these things have to be consistent along with these commutation relations, if these equations have to be consistent with these commutation relations, then you should put a minus sign here, Rs del cube P bar minus Q bar. Now there is a minus sign here, this is note, this should be noted essentially, okay. So if you take a commutator for the ladder operators essentially and try to impose quantization conditions with computation, you end up having with a negative sign for the ladder operators. Now this will lead to all kinds of problems essentially. This will lead to all kind of problems because now you cannot normally the ground state 0 is defined by the annihilation operator acting it to be A acting on is equal to 0, this is equal to 0, which annihilates the vacuum. Okay. Now if you do the same thing with C acting on 0, if I do this now, but if I do this, because of this negative sign in the commutation relations, all excited states will have created by C operator, C dagger operator created by operator will have negative norm, because it is obvious, right, because you have this negative sign. So, they have a negative norm. This is a okay, serious problem. Problem you do not want to have in quantum mechanics states with negative norm essentially, or in quantum field theory. Okay. You cannot have a negative norm states essentially, all other commutators vanishing. So, here if I impose, okay, all other commutators are vanishing, but if I impose commutators on the field operators and try to quantize them with the conjugate momenta essentially, psi dagger is nothing but the conjugate momenta, because pi, the conjugate momenta, is nothing but psi dagger, as we have seen here. You end up creating states, okay, with negative norm, which is a serious problem. Okay. So, let us stop here, and then we will continue in the next class. We will see, okay, how to get out of this problem essentially, and then we will see what are the ways out and how to quantize it correctly essentially. So, let me stop here. Okay, I will be back with the next lecture. Okay, thank you very much.